In this video, I'm going to be going through 3 questions from Anil Haja's Engineering Mechanics. These 3 questions I've put separately because they all have to do with uniformly distributed loads. Now, the syllabus says that questions on uniformly distributed loads at the HSC level have to be, they can't use calculations. Nevertheless, I think it's interesting to see if we want to have a look at these. Arnie thinks it's worthwhile going through them, so let's have a look at how we would solve this question. So the first thing I'm going to do here is I'm just going to imagine if I replaced this load with, so what I've got is a uniformly distributed load of 20 kilonewtons per metre. Now there's 6 metres, so 6 times 20 is 120, and I'm just going to imagine that's in the middle of this load. So what I would do is if I was drawing that as a shear force diagram, and this, if you wrote this down, I think in the HSC, I think this would be a pretty good approach. They can't really write a question like this as far as I'm concerned in the syllabus. So let's say they did. If you just did this, I think this wouldn't be such a bad solution. So we went up 105. So once upon a time there was a shear force diagram that went up 105, and we've been given these values. And then we went down a total of 120. Now, the thing is, we know that 120, which means that 105 minus 120 is going to be 15, right? So I'm going to be going down 15. By the end of it, it's going to be 15. Now, it's diagonal because what that means is, well, for the first metre, we went from 105, and we went down 15. So the first metre, we're 95. And then the next metre, went down, so we're now at 75, then 55. And then so on until eventually we get down to this point here. Then nothing happens for the next 8 metres, and then we're going to go down 35 kilonewtons. So here we're at 15 kilonewtons. We're going down another 35. 35 plus 15 is 50, and then finally at the end we're going to go back to 50, back to 0. And that's, we always expect to end up at 0. So a shear force diagram, what's it going to look like? I've said before in another recording, it's always a good idea to imagine what this deformation look like. It'll probably look something like that, really. There's no other forces pushing it back or forward, so it means that our curve should look something in this, our bending moment diagram should look something like this, except that we know that this area will be curved, and then here it will be probably a small amount down and then a big amount down. That's probably what I think it should look like. Something like that would be my expectation. So let's see what we end up getting. I'll leave that there as a prediction, and we'll see how close it gets. So what we have here, if we were doing this in practice, it would actually be really important to know where our maximum's actually going to line up with this, where we've crossed the axis. And we've crossed the axis some number of meters beforehand. So our diagram will look like actually up higher and then down, because our maximum has to be curving down after that, because this is slightly negative. But we should be able to find where that thing crosses. To be honest though, that's beyond the level of the HSC, finding out where that line crosses. So we know that the total value of this is, well, so it's 120 divided by 105. I mean, we probably should find out exactly where it is, because this is relevant to them. I said it's, I'm getting a calculator out. 105 divided by 120 times 6 will give us 5.25 metres is where we're going to have our maximum. You don't need to worry about how I found that. That's beyond the HSC level and how I found that. But so then this area is going to be, our maximum peak is going to be that number times 105, and then because it's a triangle, we divide by 2. So we're doing the height times the width divided by 2 will give us an answer of 275.6 kilonewton meters. And then it's going to dip down a little bit. then to work back here, I'm going to go the opposite direction. And this is, I think, good theory to figure out. We've got 50 times 3, so that's going to be 150 at that point, 150. And then this line is just going to join up somewhere in between those. I could figure out, if I need to find out that point, I could say, well, that's going to be 150 plus 15 times 8 plus 150 is 270. And so we've actually found all of the bending moment diagram. But like I said with all of these, they're beyond the scope of the HSC. This might be an interesting exercise to say, oh, that's interesting to see how we could solve it. But and we can see that that matched our diagram pretty closely. I haven't drawn this to scale, so obviously that might even be more correct than this one. But my prediction was pretty good there. Okay, so the next question we're going to look at is 53. It is a simpler question because the whole beam is uniformly distributed load. Again, they've given us the reactions, which makes life easier. So for question 53, it's 11 metres, and there's a uniformly distributed load all the way across of 30 kilonewtons per metre. And we've got two reactions. So we should be able to figure out the reactions. If there's 30 kilonewtons per metre, 30 times 11 is 330, divided by 2 is going to give us 165 on each side.
It also says that.
It was already also given,
Yeah.
but I just wanted to prove that we could calculate that without too much effort. So what's that going to look like? Well, we're going to have a shear force diagram. Once upon a time there was a shear force diagram that went up 165. And we know here that it has to go up 165. And we know that there's just an even slope down, and it's going to cross halfway. Our maximum bending moment's going to be halfway. But if we wanted to give a few more details, and I think this is actually a reasonable question. I think that given that they've given us this here, this question is maybe HSC worthy. I think it'd be tough. There's not technically any calculations at this level. You're really just drawing a diagram. But if I wanted to give a figure, I could say that if we went down 1 metre, well, we're going to be moving 11. So 165 minus 11 is going to be 154, and so on and so on. And you could draw what the value would be at each metre. So that's the shear force diagram. The bending moment diagram, well, we know that it's going to be curved, or parabolic, and that the maximum, I'm just going to clean that up a little bit. The maximum is going to be, I'm going to ignore that now, is going to be, this is half of 11, so it's going to be 5.5 metres, 5.5 metres. This is going to be equal to 165 times 5.5 times a half. 165 times 5.5 times 0.5 equals 453.8 kilonewton meters. Okay, so that one's not too bad. We'll then go on to the next one. 54. And we've been asked for bending moment diagrams for this one as well, right? Well, we're at 5, 4, 3, 4. 5, 4, 3,
Just the shear force
4.
diagram.
Just the shear force diagram, even better. Look, I might end up keep going with it because 23, 49, 5, 4, 3, 4 meters. We've got a uniformly distributed load for the first 5 meters, which is 10 kilonewtons per meter, I'm assuming. That's going to be 7 kilonewtons and then 15 kilonewtons. Okay. Does that all match the question?
Yeah.
Excellent. Okay, so we've got a shear force diagram. The shear force diagram, first of all, we're going to go up 49 newtons. Then we're going to go down 10 newtons every metre. So we could divide that if we wanted into 5 little chunks. Yeah, that's pretty good. 1 metre, 2 metres, 3 metres, 4 metres, 5 metres. Close enough. Okay, and we could actually dot that in. So we could say, well, here we're going to be 39, then we're going to be 29, then we're going to be 19, then then we're going to be 9, and then we're going to be minus 1. And then nothing happened. Another way of doing this, we could just say, well, it's 50 times 5 is, 10 times 5 is 50. 49 minus 50 is minus 1. You can see how I did it. You can compare the way that I did previously. Then nothing happened for 4 meters. We went down 7, so it gets us to minus 8. So minus 8 kilonewtons. And then we're going to drop down again. Minus 8 minus 15. It's going to be 23. Yep. Oh, and it should be 23 because otherwise that wouldn't work. Minus 23, and then finally up 23 back to 0. Okay, where is our maximum likely to be? It's going to be here. This is why they haven't asked us to draw a shear force diagram, bending moment diagram. Maybe they didn't ask us to draw a bending moment diagram in the first one either. I don't remember. So what we're going to get...
Just a shear force.
Yeah, that makes sense. Okay, so we've got a bending moment, then it's going to be hit its maximum about there. It's then going to go down a little bit, then down a lot, and then down a real lot. So that might actually be a little bit higher. That'd be my prediction of what that bending moment diagram should look like. Okay, not really part of the course, but hey, maybe this question will be helpful for you guys when you're at uni and you want to start learning about more advanced bending moment diagrams. We're done.